People have always wondered what's out there. What's on the other side of an ocean, or what's on the other side of the universe. And when it comes to space, we've done a lot more than wonder. Our curiosity began with people staring up at the night sky with just their eyeballs and making mental notes of how things changed as the weeks rolled by. Today, we're hurling telescopes up there to study the oldest light in the universe, and using a telescope the size of a planet to capture an image of a supermassive black hole 55 million light years away. Sounds impressive, right? I mean, it is. But those telescopes are already becoming outdated. In the coming decades, even more powerful ones will join a global campaign to uncover the secrets of the cosmos. On the ground, behemoths like the giant Magellan telescope will investigate everything from distant planets to dark energy. An ocean away, a field of what looks like metal Christmas trees will assist the world's most powerful radio telescope in peering back to the births of the first stars. But why stop there? Up in space, telescopes like Origins and Athena will make iconic images of galaxies and nebulas look like pixel art by comparison, all while painting pictures of things that are normally invisible to the human eye. And some scientists have dreamed up even wilder ideas, like using craters on the moon as huge radio telescope dishes, or even the sun itself as a lens. To accomplish all of this, humanity is working together, putting together international teams to conceive and build things that wouldn't have been possible a generation ago. And we are collaborating ourselves. I'm Astro Alexandra, and this is the stuff I think about constantly. I'm a science communicator who mostly talks about space and the cosmos. So I'm thrilled to be working with SciShow to explore these amazing feats of engineering. Come with me as we peer through the telescopes of the future. Okay. When you picture a telescope, you probably think of a tube with a couple of mirrors and lenses tacked on to one or both ends. And that design has been as resilient as Dolly Parton. Many of the telescopes that engineers across the world are designing today use those same basic principles. It's just that soon, they'll be large enough to park a jet on. Meet the Extremely Large Telescope and the Giant Magellan Telescope. Their names aren't exactly creative, but they definitely make up for it in engineering. Assuming everything stays on schedule, the ELT should go live in 2028 and the GMT in 2029, and they'll both be hanging out in the hottest neighborhood for ground-based telescopes, Chile's Atacama Desert. The desert is high, dry, and sparsely inhabited. With less atmosphere to stare through and little to no humidity, it's the perfect place for stargazing. Well, minus the massive earthquakes, but I'll get to that in a minute. It might be surprising to hear that both the ELT and the GMT are designed to do basically the same thing: capture mostly visible light, as well as some ultraviolet and infrared wavelengths, from some of the universe's most distant objects. That also means their targets are similar, but these behemoths are jack of all trades. It's impossible for them to run out of questions to answer. Why is the observable universe not only expanding, but expanding faster and faster? They're going to try to answer that. Want to know how the supermassive black hole at the center of the Milky Way affected the evolution of our galaxy? They're going to try to answer that. How likely is it that alien life arose on planets orbiting the twinkling lights in our night sky? They're going to try to answer that. Scientists are planning to use these telescope titans to study everything from our own solar system to planets in orbit of other stars to infant galaxies at the edge of the observable universe. They'll even test if what we consider fundamental physics is really fundamental everywhere. Because if you're investing billions of dollars and decades of engineers' time into a single massive telescope, you're going to want that telescope to uncover as many of the universe's secrets as possible. And having two of those generalist telescopes to tackle these questions will help us get more data faster. After all, if you only have one telescope, the proverbial line that astronomers have to stand in before they get to collect the data specific to their research project is twice as long as if you've got two. All major telescopes require astronomers to apply for a certain number of hours to use them. There simply aren't enough hours in the day, or rather night, to go around. So if you have more high-quality telescopes, it means the people who approve those applications don't have to be quite as choosy. And maybe, just maybe, the scientists who are used to waiting decades for their equipment to get built and collect the data that they'll then spend years and years picking apart won't have to wait quite as long. So the ELT and GMT have the same general mission, but how these telescopes will approach their missions is anything but identical. On the one hand, you have the extremely large telescope, which put all of its skill points into mirrors. Its primary mirror will be made of a whopping 798 individual ones, all working together to create a structure 39 meters wide. It will collect tens of millions of times more light than the human eye. And getting almost 800 mirrors to work together is somehow even harder than it sounds. To get the crisp, mind-blowing images that astronomers expect, the entire structure, which remember, is the size of a parking lot, can't be warped by any more than a few nanometers. So to keep all those mirrors moving precisely and perfectly in sync, engineers will use about 9,000 of the most accurate sensors ever used in a telescope. This is all a huge contrast to the giant Magellan telescope, or the GMT, whose mantra is less is more. Like the ELT, it will have a big primary mirror, although it will be just over 25 meters wide instead of nearly 40. But that mirror will be made of only 7 pieces arranged in a flower shape. If you've ever tried to coordinate anything, you'll see the advantage here. Like herding first graders, it's way easier to get 7 mirrors to move in formation than it is 798. The catch is, if you're putting all your eggs into 7 baskets, those baskets had better be flawless. To that end, each mirror for the GMT takes 4 years to make, and half of that time is just polishing them. Now, before you feel sorry for the poor grad student hovering over a giant plate of metal-coated glass, rubbing it with a cloth, you should know that modern facilities are a little more complex than what old-school astronomers were rocking. Human hands are certainly involved along the way. For example, they place individual chunks of glass into the mold to make sure it spreads out nice and smoothly when it's time to melt. But machines have to do the really hard work of polishing, because in the end, the biggest peaks and valleys on the mirror surfaces have to be smaller than 1/1000th the width of a human hair on a mirror that's larger than a monster truck. These will be the largest, most difficult to produce mirrors ever made. And in September 2023, fabrication began on the 7th and final one. Let's cross all of our fingers and maybe a couple toes to make sure it all goes off without a hitch. But those 7 mirrors aren't the whole story. Because after light hits them, it's not a straight shot to the scientific instruments. Along the way, the light gets bounced off a second set of smaller mirrors to help correct for the atmospheric distortions that make stars twinkle. Because while a twinkling sky might be beautiful to you or me, it makes the signal that a telescope is trying to track smudged. Not beautiful at all. Elsewhere in the desert, the extremely large telescope will also have additional mirrors, but in extremely large fashion, it'll have 4 of them, including the largest convex mirror ever produced. So, to pick up light from the distant corners of the universe, the ELT went all in on mirrors, and the GMT went all in on precision. I don't know about you, but I think that's awesome. Not only do we get a little variety in our telescope designs, it's a cool demonstration of how you can throw 2 teams of scientists into 2 rooms, give them the same mission, and see 2 completely different ideas come out. It's human creativity at its finest. And that creativity also appears in how these teams approached their shared enemy: earthquakes. The Atacama Desert might be high and dry, but it's also one of the most seismically active places on Earth, which is bad news no matter how many mirrors your telescope has. So besides having to create incredibly advanced telescopes, engineers also had to build incredibly advanced houses to keep them safe. The ELTs looks like a jungle gym of steel bars, strong enough to hold all those mirrors, their supporting instruments, and stay perfectly stable even when seismometers are shaking like my hands after coffee number 5. Meanwhile, the GMT went full-on sci-fi. It'll live in a spinning 22-story smart home with a damping system that's so powerful the telescope can withstand a magnitude 8 earthquake, something strong enough that it could destroy entire communities. Nothing like that has ever been built for a telescope before. When you see fancy space pictures in the news, this is the kind of stuff that often gets left out. The work of hundreds of talented people designing things like earthquake damping systems and mirror sensors. You might also miss just how international these endeavors are. Back in December of 2023, the first 18 segments of ELT's primary mirror were shipped to Chile all the way from France, where they were polished after being created in Germany. And the GMT's primary mirrors are fabricated in Arizona, but its secondary mirrors will be birthed in France and Italy. All in all, dozens of countries around the world are involved in these projects somewhere along the line. It really takes a village, and learning about this reminds me that for every gorgeous galaxy picture, there are probably a dozen technological advancements and 100 human careers that go unseen. That might sound like overkill if all you want to do is take a pretty picture, but remember, astronomers aren't trying to give humanity a bunch of new desktop backgrounds. I mean, they're not just trying to give us a bunch of new desktop backgrounds, but I think they like that part too. They're asking questions of the universe and building equipment that is sensitive enough for us to understand the answers. Lucky for both the ELT and the GMT, this isn't a two-telescope job. For one thing, humanity still has a fleet of veteran ground-based observatories we can rely on. But there's also another up-and-comer that's even bigger. It's so large that once it's finished, it will span 2 continents, and part of it looks suspiciously like a Christmas tree farm. This is the Square Kilometer Array Observatory, or SKAO if you're short on time. Construction started back in 2021, and it's supposed to wrap up in 2029. Once it comes online, the SKAO will look for radio waves, which are actually a type of light, even though many of us just use them to play music in our cars. And since they're emitted by extreme phenomena like dying stars or galactic cores powered by supermassive black holes, researchers can use this observatory to study things you won't find in our neck of the cosmic woods. Specifically, the SKAO will focus its efforts on the first billion years of the universe, how the first stars were born and died, where the earliest galaxies came from, questions that are not completely different from what the GMT and ELT are hoping to answer. But radio waves are much longer than waves of visible or infrared light, so radio telescopes need to be even bigger to capture them. And if you want to pick out the small details, well, you'd need a telescope kilometers wide, and not even the engineers behind the ELT are signing up to build that many mirrors. So the SKAO will break out a different strategy that's currently used by several other telescopes around the world: interferometry. With this method, you can combine data from multiple telescopes to create one picture, like if you used multiple cameras to make a panorama of the sky, just supersized. The SKAO will produce that panorama thanks to a collection of individual bits and bobs from all over the world, but they're coming together in 2 remote sites that are an ocean apart. In South Africa, engineers will construct an initial fleet of 197 radio dishes, and in Western Australia, they're making more than 130,000 structures that look a bit like metal pine trees. Their spindly arms will absorb lower frequencies, also known as longer wavelengths, of radio waves more efficiently than your traditional dish shape. And those incoming radio waves will trigger electric currents to flow that ultimately send signals to computers that can process the data. With more than 130,000 detectors working together, that's a lot of data. Over 700 petabytes every year. It's countless chances for astronomers around the world to collaborate and learn something new. But it's also countless engineering headaches to get them that data. See, interferometry takes more than just turning some mechanical eyes to the sky and clicking the shutter button. Like, you know how the Earth spins? Yeah, that's a problem. It means that radio waves from one distant space object will hit 2 spots on the planet at different times, so you need to use computers to account for that time delay, which gets messy if you're trying to combine data from 100 telescopes, let alone 100,000. It'll require fancy technology like atomic clocks to timestamp exactly when each bit of data comes in, supercomputers to stitch all the separate bits together, and telecommunications hardware that can handle the transfer of everything to regional archives located around the world. And someone, or rather several hundred someones, will have to build that fancy technology. But if engineers can pull it off, we have the potential to learn a ton. One of the exciting things about astronomy is getting the chance to understand a little bit more about where I came from, why the universe is the way it is, and where all the elements came from that make up my fingers and toes and everything between my fingers and toes when I go like this. It should be fairly evident by now that these massive Earth-based telescopes require a lot of planning and collaboration to get them off the ground. So you can imagine how complicated things might get when you need to construct a telescope that has to literally get off the ground. That's right, we're turning our attention to the space telescopes of the future, ones with fuzzier launch dates in the 2030s and beyond, that let us take a little tour of the electromagnetic spectrum. Because each kind of light, from radio waves up through gamma rays, can give us unique insights insights into all the different objects sprinkled throughout the universe. But every telescope, whether it's on the ground or above our heads, is designed to capture just a fraction of all those wavelengths. Take the Origins telescope. It's scheduled to be in development and testing until at least 2032, with a tentative launch date in 2035. Like our current hottest next-gen space telescope, JWST, Origins will observe much of the universe's infrared light. And perhaps its most important assignment will be looking at rocky exoplanets orbiting at just the right distances from their stars so liquid water can exist on their surfaces. Origins will check the air of those exoplanets to see if they could actually be habitable to life as we know it. By studying exactly which wavelengths of infrared light pass through an exoplanet's atmosphere, Origins will determine if that alien air contains compounds like methane, carbon dioxide, ozone, and water vapor, and if so, how much? With this data, researchers will have a much clearer picture of whether a rocky world is more like Earth, or freezing Mars, or scorching Venus. They'll also have a pretty good idea of what resources might be available for any alien critters that might call that world home. Now, the JWST can also probe exoplanet atmospheres, but Origins will be able to detect longer wavelengths of infrared light, called far infrared light, which means it can search for signals that the JWST would miss. In fact, when it comes online, it will be 1,000 times more sensitive than any existing far infrared telescope. 1,000 times. And how will Origins pull off that feat? By cooling things way down. See, it's not just planets or other astronomical objects that emit heat as infrared radiation. You do it. I do it, telescopes do it too. So unless you want a bunch of thermal noise to drown out the faint signals coming from light years away, you gotta keep your infrared telescope frigid. For instance, the mid-infrared instrument on the JWST needs to stay below 7 Kelvin to operate properly. That's negative 266 degrees Celsius. And seeing in far infrared requires even colder temperatures. For the JWST, engineers built a state-of-the-art cryocooler, and Origins will use a similar design to get its far infrared instruments down to just 4.5 Kelvin. These cryocoolers are basically the world's most advanced refrigerators, manipulating some super chilly helium gas to sap away the heat made by the telescope's electronics. But that's not all. Origins' cooling system had to be designed so that it can do all of that in microgravity without noticeably vibrating and messing up the images it's trying to capture. Try getting your mini fridge to do that. Pair that cryocooler design with the best infrared sensors engineers have ever built, and Origins is about to make us so good at detecting infrared light that we can't even guess at everything we'll discover. But let's leave Origins to its R&D and move up the electromagnetic spectrum to near-infrared, visible, and ultraviolet light. One space telescope currently studying all those wavelengths is the Hubble, which has been blowing our minds since 1990. But given its veteran status and the fact that technology has progressed so much over that time, researchers have already started to imagine its replacement. For example, back in 2019, multiple teams submitted their designs to the US's National Academy of Sciences for the 2020 Astrophysics Decadal Survey. Basically, every 10 years, some very important astronomers and policymakers get together to agree on a bunch of space stuff, like what questions are most worth investigating and what instruments should be funded to get the job done. One of these telescope proposals even provided 2 different size options, in case one was a bit overly ambitious, and whew, the larger version was certainly ambitious. A 15-meter primary mirror in space. That's more than twice the width of the JWST, which is already the current record holder for the biggest mirror up there. These 2 telescope designs went by the name LUVOIR, or the Large UV Optical IR Surveyor, which tells you a lot about what you need to know about them. And if you couldn't notice from the mock-ups, their design borrows very heavily from the web. Which, I mean, fair enough. Engineers already figured out a way to build a super sophisticated telescope that could be packed into a rocket that's too small for it, survive delivery to the near void of space, and assemble itself into working order without a single human within 1.5 million kilometers. Go with what works. But here's a cool detail. According to the proposal, LUVOIR would also be modular, which means that over the years, scientists could swap out old instruments for new ones. And getting the max mileage out of your space telescope is definitely desirable. Just look at what Hubble's been able to do thanks to all those service missions. In terms of science, LUVOIR was meant to cast a broad net, looking at all kinds of phenomena. It's basically the same broad range of stuff that the ELT and GMT will be checking out beneath the Chilean air, because they're all studying the same kinds of light. But if you're looking for something a bit more specialized, you may be interested in a much smaller alternative, Habex. In what is definitely the plot twist of the century, the proposed habitable exoplanet observatory would spend about half its time looking for habitable exoplanets, but it would do it in style thanks to its incredibly novel sunglasses. Lots of telescopes looking for exoplanets made use of a stellar coronagraph, which blocks light coming from a distant star so that the telescope can pick up the much fainter light of any planets orbiting around that star. It's the same idea behind putting your sun visor down when you're driving into the sunset, except the coronagraph does a way better job. Now, most of these fancy star visors are attached to their telescopes, but Habex would be fashion forward. Because not only would it have a coronagraph inside it, it would have a whole separate spacecraft called a star shade floating almost 77,000 kilometers away, and coordinate with Habex using radio waves and laser beacons. That way, the star shade could be adjusted depending on what data Habex was trying to capture. No telescope has ever come with its own separate support spacecraft before, so this would be a whole new ball game, and a whole new budget game, because none of these proposals was going to be cheap. In 2021, the Astro 2020 report was shared with the public, and in it we got the official recommended specs for the unofficial successor to Hubble. The authors want a telescope launching by the 2040s that's similar in size to the JWST, which means it'll be larger than Habex, but smaller than both LUVOIR designs. And the sticker price they want to aim for? $11 billion. That might sound like a lot, and it is, but it's roughly the same cost as the JWST and promises to give us an even richer view of the cosmos. So we've got upcoming space telescopes looking at longer infrared light, shorter visible light, and even shorter ultraviolet light. Why not get even shorter? Meet Athena. Unlike the previous space telescopes, whose design teams are primarily based in the US, this project is coming out of Europe, plus some assistance from NASA and Japan's National Space Agency, JAXA. It's due to launch around 2035, and it will be the largest X-ray telescope ever built. X-rays are high-energy, short-wavelength light given off by super hot objects in space, like the gas found around black holes. But almost all of the X-rays that rain down on us from space are absorbed by Earth's atmosphere. That's very convenient for our easily damaged DNA, but it's less than convenient for astronomers. So if we want to study the astrophysical phenomena that throw out a bunch of X-rays, we need to throw our X-ray telescopes above the atmosphere. But that's not all. An X-ray telescope can't rely on the same tricks we've developed for infrared and visible light telescopes. X-rays have so much energy, they don't reflect off mirrors the same way. If they hit a mirror straight on, they'll slam straight into it, like arrows embedding in a target. X-rays only reflect when they hit a mirror at shallow angles, grazing off the surface like a rock skipping across a pond. So, to build an X-ray telescope, you basically want your light to bounce off the walls of your telescope tube towards the detector, not a slightly curved mirror at the back. And instead of making a better telescope by making a bigger one, your X-ray telescope can capture more detail by packing in more and more concentric mirrors. Now, this technique isn't new. What is new about Athena is how it will focus all those bouncing rays into one coherent signal, silicon pore optics. Engineers are using machines to cut tiny grooves into tens of thousands of silicon wafers. Each wafer is then quality checked by a human, coated with a mirrored finish, and precisely bonded into a big stack with the help of a robot. The grooves all line up and form a tunnel that tapers towards a single point. So when the X-rays enter the grooves, or the pores, they'll be focused into a single sensor to create a clear image. From Athena's stacks of X-ray bouncing plates to the continent-spanning array of radio-sensing Christmas trees, scientists have come up with some telescope designs that look pretty weird. But things are going to get weirder. There are proposals for telescopes out there that look even less like the ones of yesteryear. We can't cover every awesome idea, so here's a little speed round of things that might be coming. On the tiny end of the super futuristic ideas scale, you have SPIDER, a project by the company Lockheed Martin. You know how space telescopes are big and heavy, so they cost a good chunk of cash to launch into orbit? Well, SPIDER is all about getting rid of that problem, miniaturizing the tech without sacrificing the image quality. And to do that, the final design would involve hundreds or thousands of super thin lenses, each smaller than a millimeter wide, working together via interferometry just like the continent-spanning square-kilometer array does. So unlike real spiders, this spider would have its own version of compound eyes. If the technology ever gets off the ground, it also won't resemble your traditional space telescope, you know, a big tube with a bunch of detectors sticking out the back. You could arrange these lenses into all kinds of flat shapes, whatever made sense for your mission. And get this, the whole lens system could be printed with lasers in just a few weeks. So SPIDER's looking over there at the giant Magellan telescope with its 4-year timeline for each of its primary mirrors and laughing. That said, the most recent news we could find on SPIDER came from 2017 when Lockheed Martin got their prototype to capture some images. So this isn't a project with a scheduled launch date or even a fully designed mission. But it does go to show what engineers are thinking of and what telescopes could look like in a few decades. Or maybe the pendulum will swing in the opposite direction and we'll develop an idea called the Lunar Crater Radio Telescope, which is exactly what it sounds like. The far side of the moon is packed with craters, and researchers have suggested turning one of them into a radio telescope dish. Because who needs interferometry to link up a bunch of smaller dishes when you can convert a massive crater into a single giant one? The idea is to find a crater that's a few kilometers wide and use a fleet of robots to install a 1-kilometer telescope dish inside of it. Since radio waves have super long wavelengths, you could even build it out of wire mesh without sacrificing resolution. And hey, that lower lunar gravity is bound to make construction of a giant metal telescope easier too. Not only would a crater telescope's massive size allow us to capture radio images with a solid amount of detail, but because it's on the moon, it could detect some radio wavelengths that we can't see from Earth because they're reflected by the atmosphere. We have a lot to learn about these types of waves because we haven't had much experience looking for them. Since radio telescopes have to be way bigger than other telescopes to get the same image quality, we haven't really been launching them into space. That said, considering our most advanced space rovers sometimes have a hard time crawling over rocks on Mars, it might be a long shot to get them to install a 1-kilometer wide telescope on the moon. But maybe they could install a liquid mirror telescope instead. That idea has been proposed a few times over the decades, and it's somehow even more out there. A liquid mirror telescope is basically a spinning puddle. If you steadily rotate a dish covered in shiny liquid, the forces created from that spinning will shape your puddle into a curved mirror. Sure, you need to have a great damping system to prevent any unwanted jiggles, and a system that keeps rotation speed absolutely constant, but it does get you off the hook for grinding your own mirrors. You might be surprised to hear this isn't hypothetical. The idea was demonstrated using liquid mercury all the way back in 1872. And in 2022, thanks to a collaboration between institutions in India, Canada, and Belgium, a new liquid mirror telescope debuted in the Himalayas. But more lofty proposals have called for taking this technology and building an infrared telescope on the lunar surface, where there's little to no heat coming from Earth to interfere with the signal, and no appreciable atmosphere, wind, or seismic activity to disturb the big, spinning puddle. But you don't need, well, a telescope to see the enormous challenges here. Of course, experts would have to figure out how to install one of these things on the moon, but they'd also have to invent a brand new kind of liquid mirror telescope. That's because the few liquid mirror telescopes we've operated over the decades have almost all used mercury. But to keep mercury in a liquid state, it has to be warm enough. And that warmth would be enough to blind an infrared telescope. So a lunar version of this telescope would require a liquid that is both super reflective and won't freeze solid when temperatures hit minus 200 degrees Celsius. If nothing's ringing any bells for you, well, scientists have struggled to identify the right substance too. One team of researchers proposed starting with a liquid that goes by, well, this mouthful, and then coating it with a thin layer of chromium and then silver to make it shiny. Which means installing a liquid mirrored telescope on the moon might be just a little more sci-fi than a giant crater radio dish. But I can't end this segment without mentioning what might be the most sci-fi telescope idea that scientists have come up with. It's so wild, we've talked about it before over on SciShow Space. The idea is to turn our sun into a telescope. Yeah, the big ball of blinding light you'd normally think does the opposite of help us study the night sky. Because here's the thing about the sun. It's massive, and objects with mass warp the space around them, like how your mattress sinks when you get into bed. So, as rays of light pass by the sun, they get bent just like they would as if they had passed through a gigantic lens. This means that we could build a telescope out of the sun, taking advantage of its mass to see way out in the distance. I'm talking about the ability to look at an Earth-like world 100 light years away and see continents. Unfortunately for all us science fiction fans, we're nowhere near that particular future. For one thing, we'd have to send the detector half of this sun-based telescope out into the depths of the solar system, farther than any spacecraft has ever reached to get that kind of resolution. And you'd need a whole fleet of detectors spread across the solar system to look in different directions. A telescope like that is certainly a stretch goal, but I'm optimistic that one day humanity will be able to reach it. Our ways of seeing farther have gotten, well, pretty mind-blowing. I like to imagine stumbling through some rift in time back to 1610, after worrying about whether or not I'd ever get to come back to a world with air conditioning, indoor plumbing, or a knowledge of germs. I'd visit one of the early inventors of the telescope, Galileo. I'd ask him to show me his new sketches of Jupiter's moons. I'd ask him what made him think of turning a telescope towards the sky in the first place. And despite it being a violation of the Temporal Prime Directive, I'd do what every Star Trek captain would do anyway, and tell him that centuries from now, scientists will be using telescopes larger than he could fathom to study the origins of the cosmos. And then I'd realize he didn't speak English. But hopefully, we could connect over our shared sense of wonder and curiosity. Because no matter when or where we live, humans are curious, creative, and wonderful. We want to understand our place in the universe, and that means understanding what the universe is like. So far, rising to that challenge has meant making bigger and bigger mirrors, developing new techniques to capture more kinds of light, and putting our instruments in farther flung places. But the telescopes themselves aren't the point. As amazing as they are, the Extremely Large Telescope and the SKAO and whatever we might do on the moon are means to an end. With any luck, the discoveries we make together will be even more spectacular. This episode was brought to you by SciShow's patrons. For every 10,000 people who enjoy the channel's videos, only one supports it on Patreon. If that one person is you, thank you. SciShow could not do it without you.